We are Group 37, and this is our project StrikeSense. And this is our final presentation. Our all-star team is composed of myself, Timothy Azenord, Landon Wright, Benjamin Bolton, and Shem Filzeme, and we are even split between computer engineer and electrical engineers. So the motivation and background for this comes from my experience as a fighter and as a trainer. I see a lot of people want to get into martial arts, yet once they start, they don't know what direction to move in. So our goal with StrikeSense was to provide a way for martial artists to track their training, be safer along the way, and kind of give them a direction to move towards. We wanted to do this in a non-intrusive way, and our kind of motto was we want users to feel no difference during the training and all the difference afterwards. So our technical goals and objectives was to create two IMU designs, one with an IMU, heart rate monitor and MCU, and the other one without the heart rate monitor. We also aim to design a deep neural network architecture that took input from IMUs as well as took input from pose estimation models and used it alongside an LLM to classify strikes and to provide combo predictions and recommendations.
Hello everyone, my name is Benjamin Bolton and I am one of the electrical engineers in Group 37 working on the StrikeSense project. Today I'm going to be going over some of the hardware components, our decisions in choosing them, and the final product. Starting here with the physical product description, how does the final product actually look? So the StrikeSense module is a wearable device that attaches to the user's wrist via two straps. It consists of 4 boards. We have our main board, which has our MCU and a majority of our peripherals that handles the majority of the work. And under that, we have 2 regulator boards. These are for the different power levels of our peripherals on the main board. Coming over here, we have a heart rate module in the back. From the physical picture, you can see it's these pin headers where it attaches. And this allows the user to reach over with their other hand to get a finger on that heart rate module and measure their heart rate during the exercise. All of this is powered by an 18650 protected cell, which attaches right here to the right. And down here at the bottom right, you can actually see our final project picture. If you want to take a look at that, we will be going over all of these components in the next couple of slides. In this slide, we have our detailed hardware block diagram. On the right side here, you can see I've broken it into 2 main paths to make it easier to understand. Firstly, I'm going to be going over our power path where we have our 2 sources. We have our 18650 protected cell, which is the power source that is used when the device is actually in operation and on the user's wrist. But we also have our USB-A connector. When we are debugging or programming the device further, we have it powered through this, and we can write code to the ESP while it's powered and test it then and there. To determine which power source we want to use, we have a PowerMux IC, and what that does is basically the way the pins are configured, we have a priority, and in our case we chose our USB-A to be prioritized. So whenever that USB-A is plugged in, the device knows to pull power from there, and whenever it is not plugged in, the device knows to pull from the battery. Following that, the PowerMux is going to feed whatever power source is being used into our regulators. And the reason we need regulators is because some of the peripherals are at 3.3 volt power level and some are at 1.8. You can see the arrows here depicting which uses what. That's it for the power path. Next, we have the data path, which also starts at the USB. So to get our code from the computer to the actual onboard ESP32, we need to translate it to a format that the ESP understands. To do this, we use a USB to UART chip. And once the code is actually on the ESP32, we want it to communicate with our peripherals and then give data back through the USB to UART chip to our computer. The point of these 2 level shifters here is the ICM, which is our inertial measurement unit, and our heart rate module both operate at a 1.8 volt logic level. However, the ESP32 is configured to 3.3 volts. So these level shifters translate the logic levels so we're still able to use them with the ESP's 3.3 volt logic level.
slide highlights the main specifications and performance targets for our system. First, our device achieves about 85% strike accuracy, which means it is reliable to identify different strikes. And it also provides combo recommendation based on the user's least thrown strikes. So for instance, if the user throws 5 jabs in a row, it'll start suggesting an uppercut in the mix. The system includes a heart rate monitor with the ability to detect heart rate in under 5 seconds, and with an experimental accuracy of about plus or minus 2 beats per minute. From a design standpoint, the board remains compact with full size 82 millimeter by 39 millimeters, while also keeping the total weight of under 140 grams per wrist unit, which allows comfortability for the user. For usability, the system supports at least 1 hour of continuous operation with a projected battery life of 17 hours, with a 95% success rate for packet loss in data transmission. Lastly, the total bill of materials is about $553.20.
In this slide, I'm going to be breaking down the core functionality of the StrikeSense module and how it uses the IMU, which is the inertial measurement unit, to determine between different types of strikes. So on the left here, for the input, you can see as the user is wearing the StrikeSense module and decides to throw a punch, the IMU peripheral is going to gather data, motion data, in the form of acceleration, rotation across multiple axes. That raw data is then going to be transmitted via Bluetooth from the ESP module to a nearby computer, which houses the StrikeSense backend. In the backend, we have a machine learning algorithm that is going to interpret the raw data from the IMU and try to classify that between 1 of 4 different strikes. The strikes here we have are jab, hook, uppercut, and elbow. And once a machine learning algorithm reaches a certain confidence threshold at the strike being thrown, it is then going to display on the computer that strike. And you will have a recorded history of all of your strikes throughout the session. This data is very helpful for the fighter to determine patterns in their fighting, or perhaps to identify a strike that they are not throwing as often, and they're able to gather important data from this. In this slide, I'm going to be breaking down the specifics of the IMU we chose, and that being the ICM 2094B. This IMU was a really easy choice for us because of 2 things. 1, its power consumption, and 2, the fact that it is a 9-axis IMU. So a 9-axis IMU contains 3 peripherals within it, and those are an accelerometer, a gyroscope, and a magnetometer. These 3 peripherals all gather their own motion data. The accelerometer is going to give us acceleration data in a specific direction, the gyroscope rotational data, and the magnetometer actually functions as a point of reference for this motion data, so you can see which direction it's actually being recorded in. And to have a 9-axis IMU was important because the more data, the easier it is for the machine learning algorithm to interpret the type of strikes. So that, alongside with the fact that it was a 2.5 milliwatt device, made this a no-brainer. There weren't any other IMUs that really rivaled this one. It also has the most data online as far as like resources, how to wire it, any tips, any troubleshooting. It's also a very small package size, 3 by 3 by 1 millimeter. So we didn't have any issues with this IMU taking up space on our device. And the final selling point was the price, of course, $5 to $7 per chip. We were actually able to get ESP32 dev kits from Amazon that had the chip on board. So we were able to both test the IMU and the ESP32 by desoldering from these dev kits, and that allowed us a quick shipping time and troubleshooting time. So this was the device we chose, and it has worked great. For the heart rate sensor module, we went with an IC called the MAX30102. What this is a PPG pulse oximeter module, and basically it consists of LEDs and a photodetector. And when covered up, the LEDs are going to shine into whatever is covering them, and the photodetector is going to absorb that light back. We found it was best to cover it with the finger, because that's what led to the most accurate results. And within the code, based on the amount of light absorbed back into the photodetector from each LED, that translates directly into parameters such as blood flow and blood oxygen level. Using supporting libraries, we were able to interpret that data and receive a clean graph that shows pulses, which directly correlated to the heartbeat. So one thing we had to tackle was level shifting. All the dev kits come with a level shifter on board, and we decided to replicate that by using the same level shifter that we used for the IMU, and we put that on the actual IC. Initially, it was much larger for troubleshooting, but our final form factor was about 14 millimeters by 12.5 millimeters. We are very pleased with this size because it's smaller than any of the dev kits you're able to find online for this IC. And I think it resulted in a very clean looking final product that also functions very well. Like I said, the supporting libraries and documentation for the MAX 30102 were very extensive, so this allowed us to learn a lot more about the actual physics going on and modify our code to get accurate results. We then calibrated our code throughout the entirety of the project, and in the end, we were able to get about plus or minus 2 beats per minute accuracy when compared to other heart rate sensors. Another strong selling point is the ultra low power consumption for this device, around 600 microamps, which was very minimal in comparison to other peripherals in our circuit. Same thing, package size is very tiny, and we were able to create a very tiny PCB from that. And then also the PCB, the dev kits on Amazon were $8 for 3. So we were able to see how they laid these out. We were able to unsolder, and we had quick shipping times, so we were very pleased with the price on that.
Selecting the ESP32 was a straightforward decision after evaluating several alternatives, including solutions from the Raspberry Pi family, Arduino class microcontrollers, and STM32 devices. Each option was analyzed based off of processing capabilities, wireless support, power consumption, memory availability, and development complexity, both in terms of PCB design and programming. So why not the Raspberry Pi? Although powerful, Raspberry Pi devices require a Linux OS, have significantly higher idle power consumption, and introduce non-deterministic timing, making them unsuitable for real-time IMU sampling in a battery-powered wearable system. So why not Arduino? While simple and easy, Arduino class microcontrollers lack native BLE support, have limited RAM and flash memory, and among the others on the list have the lowest processing speeds. So why not the STM32? The STM32 devices provide a strong real-time performance. However, BLE functionality requires an external module, increasing PCB complexity, RF certification efforts, and BOM costs, and firmware development overhead. The ESP32. The ESP32 was selected both for its performance and ease of use/integration. The solution has native BLE and Wi-Fi support, provides a good balance between power consumption and processing capabilities, and has extensive reference designs and support libraries. Our specific chosen chip, the ESP32 S3 Room-1-N16R2, provides a dual-core 240 MHz processor, integrated BLE and Wi-Fi, 16 megabytes of flash, and 2 megabytes of pseudostatic RAM. This makes the ESP32 S3 ideal for real-time IMU sampling, BLE streaming, and a scalable multi-node architecture. Additionally, the S3 variant included vector instruction extensions and AI acceleration support, which provided future flexibility if we decided to move preprocessing or inferences onto the node themselves. Next up, MCU implementation. As you can see, here on the left is our ESP32 S3 Room-1U-N8 schematic. You can see on the right is a chart with the listed pins, their labels, and their functionalities.
Now we're going to discuss the power path, the R1.8 volt regulator. This is used for low voltage components like the sensors. At the core, the switching regulator is highlighted in red, which steps down the input voltage efficiently to a stable 1.8 volts. The inductor shown in blue is essential for energy storage and transfer in switching processes, allowing us to maintain efficiency while regulating the voltage. We also include capacitors on both the inputs and outputs, and the input capacitor is shown in orange, and the output capacitor is shown in green. And they smooth out the regulated voltage and reduce ripples, ensuring clean power delivery. Overall, this design provides an efficient, stable, and low noise 1.8 volt supply. And we selected this specific regulator because it fit our criteria. Now we're going to discuss the power path of our 3.3 volt regulator. This regulator powers the main components like the ESP32. The central component is the switching regulator IC, which converts the input voltage down to a regulated 3.3 volts efficiency. The inductor plays a key role in storing and transferring energy during switching, while the input capacitor helps stabilize the incoming voltage and reduce noises. We also included a feedback voltage divider network, which is used to maintain the output of the 2.3 volts. And this design ensures reliable, efficient power source for our system's digital and processing components. Now we're going to discuss our sources. This slide outlines the two main power sources for our system. We have the 18650 battery and the USB Type-A connection. The 18650 battery provides a high energy density, meaning it's compact while still offering long runtime. It is also rechargeable and cost-effective, making it a practical choice for this wearable system. Importantly, the batteries we selected include built-in protections features, so we didn't have to worry about overcurrent and short-circuit protection, which also reduces the need for extra circuitry. On the other hand, the USB Type-A connection provides a reliable external power source. It offers universal compatibility and allowing the system to be powered from most computers and chargers. It can also supply sufficient current up to around 500 milliamps. Additionally, the USB is simple to implement and physically robust, making it ideal for both development and user interaction. Lastly, we're going to speak about the PowerMux, the TPS2117. The role of this device is to manage switching between our two power sources. One of its key features is automatic switching, meaning it can seamlessly transition between the battery and the USB power without interrupting the system. This ensures continuous performance even when the power source is changed. It also has a very low power consumption, drawing only 1 microamps, which also helps preserve the battery life of the system. These are the main key reasons why we selected to keep this battery. This PowerMux. This device supports high current with low losses, handling up to 4 amps, which allows it to manage load spikes without voltage drops or instability. Overall, the TPS2117 ensures a reliable, efficient, and safe power transition system, which is critical for maintaining stable operations in both battery and USB.
An important part of the data path is the USB to UART module. What this does is it takes data from our USB-A connector, which is coming from a computer, and it translates it in a way that the ESP32 can understand. 3 big selling points for the USB to UART module we chose, which was the CP2102, were price, size, and power consumption. The price was $4 per IC, and we found that our ESP32 dev kit we used this same module, so we were even able to test the CP2102 initially before even ordering it, just from one of our spare dev kits. And we saw that working, so with the small form factor and a high data transfer rate, we moved forward. One big plus on the power consumption side of things is that the USB to UART chip has an onboard voltage regulator. We were initially going to regulate using our 3.3 volt regulator that we had. However, we found that using the onboard regulator was actually much more reliable for this chip, and it isolates it from being attached to our voltage bus during operation. So what happens is when the USB connector is attached to a computer, it's drawing power from there and regulating it. And when the USB connector is disconnected, our PowerMux knows to switch to the battery. And since the code will already be on the ESP32, this whole circuit is floating. It's not actually tied to anything and consuming power. So that was really good. It's all integrated and requires very few components. We just needed a couple bypass capacitors for stability and resistors. And we noticed that it was very reliable when testing with different computers. So the drivers required seemed to be native to at least Apple and Mac and Windows, which was what we tested it with. We never had to download any drivers, so this plug and play availability was a huge plus for this module. And yeah, it seemed to work great. We spoke to several different senior design groups from previous semesters before actually deciding on this, and everyone could vouch for this one, and we saw really good reliability with it. In this slide, I'm going to be talking about the level shifting, which is another very important part of the data path. Basically, the ICM, which is our IMU module, and our MAX30102, which is our heart rate module, operate at a 1.8 volt logic level. And the ESP32 we were using operates at a 3.3 volt logic level. So we needed something to translate between the two logic levels. And a common way to do this in electronics is to use something called level shifting. Our initial approach was to use MOSFETs as just two simple 2N222 MOSFETs can do this job. And we did go with that, and we were able to get it working. However, after discussing with our advisors, we saw that as a temporary approach, as there are more industry standard level approaches to do this. And what we ended up going with was an IC dedicated for voltage level translation. And the IC for that was the PCA9306. To configure this, you have your two data lines. As you can see, we have a 1.8 and a 3.3. We power the IC, and we have a couple pull-up resistors, and the rest happens inside. It's able to, based on our configuration of the power levels, it's able to translate from the lower level to the higher level in our case, and actually give data to the ESP32 that it's able to read. Several reasons that this approach is better than just using MOSFETs is because the PCA9306 avoids any issues you would have with MOSFETs, such as tuning or compatibility issues. Everything is internal, and this leads to cleaner and fewer errors, and also simpler implementation. This device is very plug and play. We didn't need to make an external MOSFET circuit. We just wired up the pins according to the data sheet, and we noticed a lot cleaner results from this. However, the MOSFET approach did work. This is just a more industry-ready approach that we went with, and we saw great success with the PCA 9306.
It's the LED and buzzer subsystem of our system. The LED and the buzzer provide a real-time feedback and improves overall system interaction and reliability. The LED serves as a visual indicator for the motion tracking system, and also allows us to quickly understand what the system is doing at any given moment. The buzzer complements this by providing audible alerts for critical events. If a threshold is exceeding or a fault condition occurs, the buzzer immediately notifies the user. This makes the system more responsive and practical in real-world environments. Together, the LED and the buzzer create a dual feedback system that enhances the usability and reliability. Both peripherals are controlled through GPI pins and the ESP32, allowing for a simple integration with minimal hardware overhead.
So in these next few slides, I'm going to talk about our testing process throughout the project and things that have changed or improved along the way. Firstly, I'm going to break down how we started, which was to order a dev kit for all of our peripherals. And in the bottom left here, we would set up an individual breadboard circuit for each peripheral. Following a successful test with each of those peripherals, we modeled our first prototype, which was a fully breadboarded prototype of the functional device. What we did for that was we started by testing the regulators, which we used oscilloscopes, and the load was the actual load that we were going to have. So this was where we decided to test. And when testing, we would measure for the 1.8 volt regulator around 1.781 to 1.788, very close to our intended 1.8 voltage supply. The ripple on that was around 0.8 millivolts to 2 millivolts. This ripple is very low, and it gave us confidence to move forward that this was a stable voltage regulation. Same thing for the 3.3 volt regulator. For both of the regulators, we tested with an input of 3.8 volts and 5 volts. 5 volts being our max limit because this was the power level of the USB, so this would be the max voltage experienced when actually operating. And for the 3.3 volt regulator, we saw 3.297 volts to 3.298 volts, even closer to our expected 3.3 with a ripple of around half a millivolt. Once again, this ripple was small enough to give us confidence that we could move forward with stable voltage regulation. And I don't have images of us testing the IMU at the breadboarded stage. However, we did, and we got value transmitting that we were happy to see. However, once we reached this stage, we immediately moved forward with the PCB design and purchasing. And very happy to say that once the PCB arrived and we soldered everything and put it all together, we saw the operation that was comparable to the breadboarded circuit. It started working pretty much right away with some troubleshooting from Landon, fixing a few shorts. And once that was all together, you can see this image. We powered it up and Bluetooth connected, and we saw the motion data changing as we would rotate the device. So that was our first big breakthrough on getting from breadboard to PCB and still remaining functional. One thing I'm going to go further into is the heart rate testing. I ordered a Max 30100 dev kit off of Amazon and tested it at my house. And I was able to get it working. However, the data was not really even close to a good baseline. So rather than wasting time calibrating, I did some more research, and I found that the community of people who use heart rate modules, the decision was unanimous that the Max 30102, which is the successor of the 30100, is much more updated and accurate. And I saw this in the articles and documentation, as well as the coding libraries, all being updated much more frequently. So looking into that data, we were able to refine the code for the Max 30102, and then these bottom pictures here show one of our final tests where we were starting to get to a level that we were happy with. We were using an Apple Watch to measure heart rate, and even an Apple Watch bounces around a little bit. So we were measuring 75 current, but we had just seen 81. So a change of about 6 plus or minus BPM. And with the finger on our PCB module for the heart rate sensor, we were seeing around 75 to an average of 79. So that was close enough to the Apple Watch where we were confident, and we even still did some more refining by reducing the PCB size and changing how we actually press the finger against the device to result in less movement and more accurate data, which you can see in this slide. The heart rate module PCB saw a 45% reduction in size. And this was the final data we were seeing, where the pulses were very consistent. Before this, there was a lot of noise in the graph that was resulting from movement. However, once we got to this point, you could actually feel your heart beat from your neck and watch the graph pulse at the same time, which was very cool to see. And we were measuring around plus or minus 2 beats per minute accuracy when compared to the Apple Watch. Landon went through and did a reduction in size on the main module itself as well, and that saw around a 50% reduction in size. And these were goals from our midterm check-in, was to reduce size and cost. And the website we ordered the PCBs through, OshPark, the main metric for pricing the PCBs is size. So with a 50% reduction in size, we saw a cost reduction go from 150 US dollars down to 40 US dollars, which was a great step in the right direction. Obviously, as we bring this device to consumer level, we want to reduce cost of production as much as possible. And alongside the reduction in cost, what this reduction in size did was it increased our accuracy too, as the initial device was much larger, much heavier, and harder to mount on the wrist. This led to a lot of noise from just motion when strikes weren't being thrown, or the wrist would just slightly rotate, which would lead to false strike triggers. However, once we reduced the size, the device was able to mount to the wrist much better, and we saw a direct increase in our accuracy without changing anything other than the PCB size. And this confusion matrix, Tim will go into more detail in his machine learning section, but the metric we're looking for is a clean diagonal line, and just a reduction in size of the PCB, we were able to see that reduction in size. So we were very pleased with all these changes throughout the process.
This slide shows the embedded software architecture running on our ESP32 S3 node. Starting on the left with the flowchart, on power up or reset, the system initializes all hardware, including I2C, the IMU, and the BLE SQAC. If any steps fail, the node enters a safe termination state to prevent undefined behavior. Once initialization succeeds, the device begins Bluetooth advertising and waits in an idle state until a connection is established. After connection, the node waits for a command from the client. Based on that command, it translates into either IMU sampling or heart rate sampling. In the IMU path, the system continuously collects accelerometer and gyroscope data, packets it into packets, and transmit over BLE. Similarly, in the heart rate path, it collects BPM and sends that at a lower rate. Both modes continuously run until a stop command is received, at which point the system returns to the idle state. On the right-hand side are key software components used to implement this system. The Arduino core provided the runtime and hardware abstraction. Wire.h handles I2C communication with the IMU and heart rate sensor. The Adafruit driver manages sensor configuration and data acquisitions. Sensor Fusion, Fusion.h, was used for quaternion-based orientation estimates. And Nimble BLE provided a lightweight BLE server optimized for low power communication. Finally, in terms of resources usage, the firmware currently uses about 9% of RAM and 16% of flash, leaving significant headroom for features like additional filtering or onboard processing. Wireless communication. For StrikeSense, we needed a wireless link capable of streaming IMU data in real time while maintaining low latency and low power consumption. On the left is Wi-Fi, which is designed for high throughput networking. It offers very high bandwidth but comes with unpredictable latency, higher power consumption, and increased system complexity due to the full TCP/IP stack. On the right is Bluetooth Low Energy, which is specifically designed for low power embedded devices. BLE provides lower but sufficient throughput, predictable latency, and a much simpler point-to-point communication model. For our application, we don't need hundreds of megabytes per second. We need reliable, consistent delivery of small sensor packets. Because of that, BLE is a much better fit for wearable sensor nodes. It gives us enough bandwidth for our IMU while significantly reducing power consumption and system complexity. So overall, BLE allows us to meet our real-time requirement while keeping the system efficient and scalable. Packet structure. To support efficient wireless transmission, we designed a lightweight custom packet protocol. All packets share a common structure, starting with a timestamp and a type field. The type field allows the reader to receive and determine how to interpret the payload. The main packet is the IMU packet shown at the top. It includes a timestamp, a type identifier, and 6 floating point values for acceleration and gyroscope data. This results in a total packet size of 29 bytes. Below that is the heart rate packet, which is much smaller. It contains a timestamp, type, and average BPM value, totaling 9 bytes. The status packet is used for control and feedback and includes a timestamp, type, a status code, and a battery percentage for a total of 7 bytes. Using packet structures ensure that there is no padding so that we minimize bandwidth usage and keep transmission efficient. This design allows us to stream high-rate IMU data while also supporting lower-rate telemetry and control messages within the same communication side. To validate the reliability of our wireless communication system, we perform a controlled transmission test. We modified the firmware to send a fixed number of BLE packets and used a Python client to receive and log all incoming data. We compared the number of packets sent to the number received to evaluate packet loss. As shown in the results, we expected 500 packets and successfully received all 500 with 0 missing packets. This corresponds to a 100% success rate. This demonstrates that our BLE communication is both reliable and consistent under test conditions. These results confirm that our system can support real-time sensor streaming without packet loss, which is critical for our accurate motion tracking and downstream processing.
So here we have a high-level breakdown of our system architecture. So we start with simultaneous capture with our IMU as well as our webcam. In our system, we do prioritize the IMU event detection and event classification. That's not to say that it's not done with computer vision. However, in our system, we prioritize the IMU classification in the sense that if both the computer vision and the IMU do not agree, we would go with the IMU classification. And the main purpose of the computer vision model pipeline is to provide a more holistic view, a full body view, to add context and to provide the opportunity to give frame by frame playback to show exactly where users can adjust their strikes. And once all of this is captured and the output is ready, it's then put out to the dashboard for users to use. So here we kind of have the strengths and the weaknesses of both the IMU and computer vision approach. And it's very interesting because both of them complement each other really well. The IMU gives us really strong temporal information, so it's better for figuring out exactly when a strike happened. It's also more robust to things like camera angle changes or parts of the body getting blocked in the video. On the other hand, computer vision is really useful for interpretation. It gives us replay, pose, overlay opportunities, and just a general visual context that the IMU alone simply cannot provide. So the way we structure the system is again that the IMU handles the timing and primary strike detection, while the computer vision adds explanation and potential for visual support on top of that. So here we have a good picture showing the raw data that we're working with as far as IMU. So this is the top of our data pipeline when it comes to IMU. So one thing I like to start out with is if you look, you see 3 clusters being captured here, 3 clusters of peaks, and each peak you can see represents a strike and a retraction. As a strike has 2 parts, is releasing and coming back. So that's why you see them alternate between high positive and really low negative values here. One thing I like to know specifically for this, because we're looking at a hook actually being thrown. And if you are familiar with the hook, it does rotate quite a bit. So if you take a look at the bottom left-hand corner, you can see that our z-axis, our data points on our z-axis for the gyroscope are fairly high compared to data points on the other 2 axes. And this is reflective of the rotation that happens in a hook. So this is the data that we start with. As for the computer vision pipeline, the top of that is essentially being filled up by key points extracted from video frames. While it's conceptually similar to the IMU pipeline, the data format is different. So we chose AlphaPose because it gives detailed pose estimation, also works really well since it has pose flow, which gives us temporal consistency across frames. So for a single strike, we estimate about half a second to 1 second of motion, which comes out to roughly 15 to 30 frames, depending on the clip. And since each frame returns 136 key point values, including coordinates and confidence information, one strike window ends up containing a fair bit amount of pose data. And the idea again is that this model gives spatial and temporal information to learn the structure of the strike from motion, not just from one frame. So moving on down the pipeline for our IMU model, first we take the continuous sensor input that you saw earlier, which was captured in windows. So meaning um, we would throw 10 strikes consecutively for one window and then close that window and then open the window again and then throw another 10 strikes consecutively. So you would take that and compute magnitude-based features for both acceleration and angular velocity. That gives us a cleaner way to summarize just overall motion intensity. When then we smooth the motion energy signal and detect local maxima, which acts as candidates for strike peaks. After that, we go ahead and reject any weak peaks that may come up and merge nearby ones so that a single strike doesn't get counted multiple times, which was an issue that we had prior. If we refer back to our demo from the end of last semester. Once we accept a peak, we create a fixed temporal window around it, and that window is what gets passed into the IMU classifier for it to classify. So moving on to our actual model architecture for our IMU model. Um, at each timestamp, the model takes in the X, Y, and Z values from both the accelerometer and the gyroscope, along with the magnitude features we computed during pre-processing. It starts at the top with a 1D convolutional stem, which first projects that input into a learned temporal feature space. After that, stacked residual convolution blocks learn the motion structure over time while also keeping training stable through skip connections. We also increase dilation progressively so the model can capture a wider temporal context and not just the immediate peak regions. Then, towards the end, adaptive average pooling compress the temporal information into a compact representation and a fully connected head all the way at the end of the process maps that learned representation to the final strike logits, which is used for our final output of what we believe the possibilities of the class could be. Excuse me, the probabilities of each class could be. So here we did implement a couple of different strategies to get the best out of our model, and we actually implemented the strategies for both models. So this is to represent both the IMU model and the computer vision model. First, we used weighted loss so that mistakes on smaller classes were penalized more heavily during training. That helped reduce bias towards more common strike classes. We trained using Atom and added weight decay to keep the learned weights from growing too large and overfitting. We did actually end up running into a bit of overfitting with the computer vision model. However, it's nothing too detrimental. We also added k-fold cross validation, so the model could be evaluated across multiple train validation splits instead of depending on just one split. And kind of visualization of this is seen in the picture in the bottom left-hand corner. On top of that, we used a specific scheduler, the reduced learning rate on plateau, to lower the learning rate when validation performance stopped improving. We also implemented early stopping so we wouldn't waste any epochs once the model had clearly plateaued. Together, we believe those choices made training more stable and helped a fair bit with generalization. So here we have a confusion matrix which shows the performance of the IMU model itself. And in this case, the diagonal entries are the correct predictions. So as you can see, the x-axis is the x-axis is the predicted label, and the y-axis is the true label. So kind of the golden line that you're looking for is this diagonal line that we see here. And what we saw is that some classes, like the jab and the hook, were learned more cleanly, while others, especially the uppercut and the elbow, um, were more likely to be confused with each other. So the main takeaway with this from our IMU model is that it's strong enough to act as the primary detection system, but the results also show why segmentation quality and class balance matter a lot. This is one of the main reasons why we kept it IMU first, but still kept the computer vision portion for supporting context. So here we have the approach and architecture for the computer vision model. We use a temporal pose-based classifier with a CNN plus a bidirectional LSTM, long short-term memory, um, and finally an attention architecture. So all of these things were put together to make our final model architecture. So the input here is, again, not raw video, but a sequence of body key points extracted over a defined strike window. So our approach with this is that we used a window size of about 80 and something called a stride size of about 60. 50 to 60, we alternate between there. And if you would imagine with me, this allows for some overlap between strikes. And this is important because it provides the in-between context that is essential for identifying strikes thrown one after the other, instead of only being able to identify strikes in isolation, which was an issue that we did encounter during training. So starting from looking at this image from the bottom, the CNN front end captures local motion features across nearby frames. Then the bidirectional LSTM models the motion trajectory in both forward and backward directions, which helps because, strike, like I said before, is not defined just by impact, but, how you lead in and how you follow through, right? The example I like to use is if you have a sibling, you guys are both fighting for a piece of food, right? It's not just enough to have your hand on the food, you have to bring it back as well, right? After that, the attention layer learns which frames are the most informative and builds a context vector from those important parts of the sequence. Finally, the context vector goes through a classification head that outputs class logits. This part is very similar to our IMU model, which are then converted into class probabilities with softmax. So here, we actually have our results. So while on the surface it may look pretty good, it is a bit alarming because there is a fair bit of overfitting going on here. So we did see a drop in performance once we did run it live. However, with the IMU model running alongside of it, it was no issue at all. So over here, I believe we had a accuracy of 98, and this dropped in testing to about 83%. And as for our dashboard, we do use the following stack. We use it's built upon Next.js, which is built upon React JS for our front end. For our back end, we use Node.js and Express, as well as Python. We do implement our APIs with Fast API, and we do have a database built on PostgreSQL, which stores the user information as well as login information.